Welcome everybody. We're going to talk about exponential and logarithmic equations. And what our goal here is that we want to be able to solve some basic kinds of equations that will involve exponents and logarithms. And to begin with, one of the most important things we can do is recall some of the properties that we have already discussed. And there are four of them that are really important to us here. These are very useful properties. The first one are the one-to-one properties. The one-to-one properties are the properties that say that, well, if a to the x is equal to a to the y, that's true if and only if x is equal to y. And likewise, for our logarithms are also one-to-one. And if you take the logarithm base a of x, it will be the same thing as taking the logarithm base a of y. That will be equal if and only if x is equal to y. So let's just see this first property in action. What we're really saying here is something like this. Say we have an equation like 3 raised to the x is equal to 81. Well, this property applies because if we rewrite the right-hand side of this equation, pen going here, 3 raised to the x power will be equal to, let's see, 81 is a power of 3 number, right? That would be the same as saying 3 to the 4th. So by this property, we have to be able to conclude that x must equal 4 in order for this equation to be true, because exponential functions are one-to-one. There are no two different values that could possibly make this equation true, so x equals 4 is the only solution. Likewise, right here, we've got the logarithm base 4 of x is equal to the logarithm base 4 of 25. Well, because they are both logarithms of the same base, we have to be able to conclude by this property that this is only true if the argument x is equal to the argument 25. And that's our solution right there. So this is actually a good example of a couple of properties that are going to be highly useful to us as we go through some of these problems after this. All right, the other property that is really useful to us is called the inverse property. And we talked about these two inverse properties early on when we first started talking about logarithms. We say they're inverse properties because we know that anytime we have a function of the form f of x equals a to the x, its inverse function is the logarithm function. So this would be the same thing as saying, well, if f is equal to a to the x, f inverse is the logarithm base a of x. And so, of course, we know that anytime we take a composition, f of f inverse of x, the result is that the two functions undo one another. And it works the other way around too. F inverse composed of f of x is equal to x based on our definition. So we're using these properties down below here in the following sense. If a raised to the logarithm base a of x is equal to x, we can rewrite this expression and say, well, this logarithm ln x is the same thing as a logarithm base e of x. And so we can say exponentiate on both sides. And if we were to, let me try this a little bit lower here so I can write this in. If we were to take the base e and raise it to the exponent, ln x, it would be the same as if we took the exponent of -2 with a base e. Really, by our one-to-one function, that would make sense. And e to the natural log of x is, by this property, just x. The e and the ln x, the two functions undo one another, and we're left with e to the -2nd. And by the way, when we express solutions that involve e, we want to express them in exact form, not the decimal form. So we would write 1 over e to the 2nd, perhaps, as our solution in simplified form, exact form. Right? This is obviously, there is a decimal that would represent 1 over e squared, but we want to leave it this way. How about this guy? I've got 3 to the x equals 15. Now, this is different from the problem that we looked at earlier because 15 is not a number that we can raise 3 to some even power and get that value. So what do? Well, in this case, we take advantage of this property right here. And the way we do it is that we say, if I were to take the logarithm of any quantity on the left, it should be equal to, and let's make it a base 3 so that I have the same log, right? We're taking advantage of this property. It would be the same as if I took the logarithm base 3 of 15. Now, in this case, right, again, we're using our one-to-one logarithm property because if I take the logarithm on the left, it will be equal to the logarithm on the right. But in this case, we have the advantage of that exponent x being left when we take the logarithm base 3 of 3 to the x, they're inverses, and we're left with logarithm base 3 of 15. Now, this is an exact value expression, so just like the other one, we could leave it in this form. But what's typically done is that we often use the change of base theorem to rewrite this one more time so that the very next step that we would take after we do this would be to evaluate the logarithm in a calculator. So we're going to write it up to the point where we can evaluate with a calculator and then leave that answer. And if I use the change of base theorem, let's say with a base e, I could say, well, the natural log of 15, if divided by the natural log of the base 3, would be exactly the same as the logarithm base 3 of 15. And so this might be the exact value answer I'd want to leave. Okay, more examples to come.